Howdy, folks. Today's lesson is the time value of money. Been talking about this for a long time. I'll be honest with you. Time value of money is probably the most important lesson you'll have. As long as you understand it, you'll see that your money can make money as long as you use it wisely. All right, so bell ringer. Let's use your computer, and I want you to do this honestly. Take the time right now to turn it off. Turn this video off, pause it, and then go on the computer and look up the time value of money and see how it's defined. And how does that time value of money affect an investment or income? Ask those questions. When you're done with that, then you come back. All right, I'll give you some time right now. Okay, so you should be back by now. You paused it, and let's go on. Before we do, though, let's talk about great things. What's great things going on in your life, my life right now? Passover starts tonight, sundown. Got to put the cedar plate out, have some good time with my family, and enjoy it. All right, lesson objective today. I can create equation models to analyze the value of accounts over time for real-world applications. So here's the thing. Before you get started, if you have a calculator, it's probably a good idea to get it out because we're going to be doing regression functions. We typically use the TI-84 Plus. If you have an emulator on your phone, that's great. That'll work for you. If you don't have an emulator on your phone, you might be able to find something that works online from your laptop or your home computer. In the meantime, though, let's get on with the lesson. The future value of an investment, the FV, is the amount it will be worth after so many months or years of earning interest. Following table lists a savings account's future values in selected years. So in other words, year 0, we have an initial balance of $2,600. After 5 years, the balance of the account is $3,201.50, all the way up to 30 years where the balance is $9,062.70. Well, how did we get there? That's kind of the question. We're going to create a scatter plot, and we're going to label the axes and scales and provide a title. Now, I'm going to do that real quick with my calculator real quick and see what it does. I will put the year in L1 and the balance in L2. So let's do that. We'll start that by going Stat, Edit, that's Enter right down here. Move my calculator up a little bit. So I've got the year in L1, the year column from this into L1, and I'm going to put the balance in L2. I'll do that real quick. So now I've got the balance in L2. So let's see what that looks like. Here's the deal, though. I want to put a scatter plot up, and let's see what that looks like. I'm going to have to turn my scatter plot on. So I've done it, and I want the X list to be L1, the Y list to be L2, and that way when I graph it, I can do it. However, I want to make sure that I see it. So Zoom 9 is how you format it, because Zoom 9 zooms to the stat. In other words, everything that's in your stat is going to be there. So as you can see, we can see what that looks like, okay? So let's go back to our slideshow here and see what it looks like there. There's our balance. That's our amount of money, the value in dollars, and then the X value is in years. And we only went 5, 10, 15, all the way up to 30 years, right? So the scatter plot for 5 years, and then for 10 years, and then 15, 20, 25, and 30. Looks very similar to what I have, okay? So what type of function do you think best models this data? You notice it's moving up in a curve that raises a little bit every time. Yes, of course, an exponential. The data increases an increasing rate. It increases a little more every time. That's considered exponential, all right? Calculate the regression equation for the given function. Okay, so let's go back to our calculator. Stat, and then we're going to go calc. We know it's exponential, so we're going to scroll down or up, if you want to exponential regression. Okay, and we'll hit enter. L1 and L2 is our list, and we're going to calculate, and it comes out with 2,600 as our A and 1.0425 as our B. And guess what? That's exactly what it says here. The regression equation for the function is y equals 2,600 times 1.0425. So what according to the model, what is the interest rate of the savings account? Now, here's what you need to understand. we take 1.0425 and subtract the 1, which is the 100% that's already in there. We're going to add 4.25%. C100 plus 4.025. 4.25 is 104.25%. So if we want to know what the amount of the interest is, we just multiply whatever the amount in the account is by 0.0425. But if we want to know how much that is, when you add that to the amount that's in the account, you multiply by 1.0425. Is the interest simple or compound, and how do you know? Obviously, we know that it is compound because there is exponential growth resulting from the previous total being multiplied by the constant multiplier, 0.0425, rather than just the initial amount. If it was multiplied by just the initial amount, guess what? It would be simple interest. All right. So, using the model, how much will the account be in the account in 50 years? The function is y equals 2600 times 1.0425 raised to the x power. So, let's go and let's put that in there. 50 years times 1.0425 raised to the 50th power. We're just going to raise it to the number of years. Should be $20,834.27. Well, I got a different value, but you see, that's exactly what it says here. The regression equation from the calculator is nearly the same we have here. Use the regression equation from the last problem to write a general formula for the future value of an investment compounded annually. We're going to use the following variables. FV for future value, T for time in years, I for interest rate in decimal form, and PV for the principal or the present value of the account. All right? So notice it looks like this. The future value equals the present value times 1 plus the interest rate times T. Now, how do we know it's 1 plus the interest rate? Now, I'm gonna give you a little hint there. If you go back a couple slides where we looked at the function to find out the interest rate, notice that 1.0425 is our constant function, not the 0.0425, which is the interest rate, because 100% of the value of the account would stay the same. If we got no interest, we just multiply by 100% every time, or 1. Now, that makes a lot of sense. But we're adding to that value the interest rate of whatever 4.25% of that value in the account is. So let's go back to where we were. Now, all of the interest investments so far have compounded and paid interest annually. However, some investments compute interest in compounding periods that are quarterly or monthly. If the annual interest rate is given and it's divided evenly into either quarters or months, how would the interest rate be calculated for each compounding period? That's pretty simple. For interest accrued annually, the interest rate is divided once. It's not divided at all. Semi-annually, we divide it twice because we calculate interest twice a year. Quarterly is 4 times a year. Monthly, there's 12 months, 12 times a year. Weekly, there's 52 weeks, 52 times. And daily, there's 365 days except in leap year, so we'll assume 365 times. So, now let's write a general formula for future value that takes into account compounding period. We're going to use the same things that we had before. Now, there's a little difference. We have another value that we didn't have before, a variable called N. It's the number of compounding periods in 1 year. So if we're compounding annually, N is 1, okay? And if we're compounding semi-annually, N is 2. And if we're compounding quarterly, N is 4. Monthly, N is 12. Weekly, N is 52. And daily, N is 365. Those all quantify the amount of each one of those in a year. So look at how this is written. The future value is the present value times 1 plus the interest rate over the number of compounding periods per year. That whole quantity is raised to the number of compounding periods per year times the number of years that the account's in, or the value of that money's in the account. So let's back up. Suppose you invest $2,600 into a savings account with annual interest rate that compounds interest quarterly. Okay? Use the formula you wrote in the last slide to determine the balance in the account after 5 years. So, PV, present value, $2,600. I, 4.25%, we'll write that in decimal form, or 0.0425. T is 5 years. It compounds quarterly, so N is 4. That's right, 2,600 times the quantity, 1 plus 0.0425 divided by 4, and that whole quantity is raised to the 4 compounding periods per year times 5, the number of years. And we get that value as $3,211.99. Let's do that in the calculator so you can see how that works. Instead of multiplying that by 1.0425, we're going to multiply it by 1 plus 0.0425 divided by 4, which is the number of compounding periods. And then we're going to raise that whole quantity times 4 times 5. And we should get the same. Yep, there we go. $3,211.99. Notice it's rounded. Whenever we're talking about money, we have to round to the penny. All right? So what are we doing here? Well, if we're calculating interest 4 times a year and the annual interest rate is 0.0425 or 4.25%, we cannot calculate the annual amount quarterly. We have to calculate 1/4 of it every quarter so that it adds up to a quarter. So that's how they get that value. Now compare this balance to the one in the table for 5 years of annual compounding. Compounding annually, only $3,201.50, but quarterly, $3,211.99 is a difference of $10.49. Now, simply because we put in an account that compounded a little more often, more frequently than once per year, instead 4 times per year, we made $10 in 5 years. All right, how much would the same savings account be worth in 50 years if the interest is compounded quarterly? Okay, so we just multiply it by 50, it's 21,526.87. And actually, if you think about that, that's more than if it was compounded annually by $692.60. You have $10,000 in an investment account that earns 4.25% annual percentage rate that compounds quarterly. How much will that account have in 5, 10, and 50 years? 5 years, it'll have $12,000. We have made $2,353.81. 10 years, we've made $15,260. We have $15,261. We've made $5,261.65. And in 50 years, we'll have $82,000 in there. And we only put $10,000 in. So if you've got a lot of years to wait, you can have a lot of money. And I'm going to put a link to the video of the Art and Ben show that Dave Ramsey does about how compounding interest works. And I'll explain it to you. I'm going to make the video my video and show you what I mean. So I'm going to launch you with this. We can see that when the frequency of the compounding period increases, the amount of accrued interest increases. What do you think happens to the accrued interest when the interest rate increases? Good thing to check. So folks, hey, listen, if there's an assignment attached to this, please get that done as soon as possible. In the meantime, be blessed and be a blessing.